Now let's do section 13.1, which is really the beginning of a much, much larger world. Again, not to quote Obi-Wan Kenobi on you, but that's how it is. So it's the ANOVA testing. So we're going to do 13.1 here, which is a one-way ANOVA. And we're going to test, we're going to verify the requirements. First, we're going to learn what those requirements are. Then we're going to verify them, and then we're going to conduct an ANOVA test. Now, notice, it's still a hypothesis test, so that part hasn't changed. Now, what is an ANOVA test? ANOVA stands for Analysis of Variance. It's an inferential method we use to test the equality of three or more population means. Now, keep in mind, this is different from what we were doing in Chapter 12. Well, let me bring that up. In Chapter 12, we were concerned about goodness of fit, which is really about proportions, right? Are the proportions matching what you think they should? Are they, matching what was assumed to be true? And then 12.2 was about proportions as well. It's saying, hey, are the proportions really independent? In other words, are the categories independent? Or are the proportions homogeneous? Are they similar across different categories? So you're dealing with proportions, which means essentially we're dealing with qualitative data, which if I didn't say before, I'll say it now. Chapter 12 was really about qualitative data. Proportions are the manifestation of that qualitative data in numerical form, which means, like what percentage said they, what percentage are red. Red is a word. Red is a nominal data, nominal level of measurement. But when you open up a bag and you can count how many red ones there are and divide it by the total, you can get a proportion for that nominal, that qualitative data. Okay? So chapter 12 was really about qualitative. Chapter 13, not so much. We're dealing with means, which means we're automatically dealing with quantitative data here. So, for example, an airline has, and before I get into that, the null hypothesis for ANOVA is going to be that the means are equal across the K groups. Now remember, that's different from what we had in chapter 12, where it was the proportions are equal. That was the test for homogeneity, kind of down here at the end. So the test for homogeneity is that the proportions are equal, right? But here it's the test that the means are equal. And the alternative to that is that at least one of the population means is different from the others. Now let's give you an example. So you have an airline has toll-free numbers for reservations. Often the call volume is heavy and callers are placed on hold until a reservation agent is free to answer. The airline hopes the caller remains on hold until the call is answered so as not to lose a potential customer. You can imagine. So what they did was they conducted a study. They had analyze when callers will hang on longer and when they'll hang up, right? So if they listen to ads about the airline and its promotions, music, i.e. that lame elevator music kind of stuff, and classical music such as Vivaldi's Four Seasons, which is great symphony. All right, so the company randomly selects one out of every 1,000 calls in a particular week. For each call, they randomly selected one of the 3 recorded messages to play, and then they measured the number of minutes that the caller remained on the line before hanging up. These calls were purposely not answered. The total sample size was 15. The company kept the study small because they don't want to alienate too many people, because they're never going to pick up on these poor 15 people. So they never picked up on them. They just played, right? So, for example, the advertisements, somebody waited 5 minutes before hanging up, 1 minute before hanging up, 11 minutes before hanging up, and so on. Music, 01463, right? Classical, somebody waited 13 minutes, somebody waited 9 minutes, somebody waited 8 minutes, somebody waited 15, and so on. So they each had 5 people in their groups, these poor 15 people total that were never, ever going to get answered. And then you have the differences in their means. So the mean here, take these 5 numbers, the mean was 5.4, standard deviation was 4.2, and so on. So there is the information in the data. Although, to be fair, you could find all of these back columns yourself. As long as I gave you these 5 numbers, these 5 numbers, and these 5 numbers, you could find the rest of it, because we all know how to find the mean and standard deviation from chapter 3. All right. What are the hypotheses for the ANOVA test? Well, it's that the average time for ads is the same as the average time for music, which is the same as the average time for classical, that they're all the same. The alternative to that is at least one of them is different. All right. So the means for the 3 groups are quite different, right? Look at these. 5.4, 2.8, 10.4. So that is quite a bit of difference. But there's not sufficient evidence to conclude that the population means differ. Why? Well, we expect some variability. So, yeah, they're different from each other, but how can we tell if this is like really significant difference, right? So we need to know if those differences are significant, if it's really something going on, or if this was just accident. So before we can do that, we need to verify the requirements to perform a one-way ANOVA, and also I need to teach you about some of the things you're looking for when you look at an ANOVA test. So the top figure shows the same data as in our table, but in a dot plot. So there you go. You can see the adds were 1, 2, 5, 8, and 11, it looks like. 1, 2, 5, 8, and 11. Yep, those are those numbers. So there they are. Okay. And then the bottom figure shows a dot plot of the data that had the same means, but different standard deviations. So this has a mean of 5.4. This advertisement ones, those 5 dots on the top line, they have a mean of 5.4. So do these 5 dots, but they have a smaller standard deviation. You can see because the spread is much less. Look at the way these advertisement ones are all clumped, as opposed to these advertisement ones that we really had, which were all spread out. Now you can see the second graph gives stronger evidence against the null hypothesis, because it's much clearer in that second graph that there's a big separation between these groups, in particular the Muzak group from the classical group. Right? You can see that they're very far apart from each other. Muzak's way over here, classical's way over here. Okay. So which of those gives stronger evidence? The second one, which is a made-up one. Our data is actually the top picture, but the second one has the same means of 5.4, 2.8, and 10.4. So it has those same means, and you can see our actual data is much more spread out. So that gives us less strong evidence than this bottom one, where they're so clearly delineated and separated from each other, which would kind of give us evidence that particularly the classical and the Muzak are different on this bottom one. The top one, it's a little bit harder to see. There's something going on there, but we'll have to parse it apart. Now, here are the requirements in order to perform a one-way ANOVA. You can't just go run around doing ANOVAs all over the place. You have to have specific things going on. There must be k simple random samples, one from each of the k populations. So like in our, well, we'll talk about ours in a second. The k samples must be independent. Again, there's that independence thing. We do very little things that are dependent. We had that one test about proportions in 11.1, and we had 11.2, which was all dependent stuff, the paired data. But that's about it. We haven't done much else. Populations must be normally distributed. Yet again, we don't work with the non-normally distributed in this course. If I ever get around to it, I might make some chapter 15 videos. That's what that chapter is, but I have not done it yet. So you don't have to worry about it. We will only work with normal stuff. Non-normal stuff is tricky. And then the populations must have the same variance. That is, each treatment group has population variance sigma squared. We're going to talk about that a little bit, but basically we're going to make the ANOVA do it for us. We skipped a little bit of that in chapter 11, unless I decide to go back and put it back in, but for right now, suffice it to say that you want the variances to be the same. There'll be a rule of thumb for that. So actually proving, here, it's like I planned it, actually proving the variances are the same is really tricky, and we could get into it. It's a whole nother test, to be honest. So what we're going to do is we're just going to kind of use this rule of thumb, which is that the largest sample standard deviation is no more than twice the smallest sample standard deviation. That's what we're going to use. To be fair, real life, it's really its own test. It's really its own thing entirely. We're just not going to work with it. We're just going to kind of use this little cheat right here to get around it. All right, so step 1. We're going to verify for our Muzak adds and classical that everything that we need to run an ANOVA is verified. So here's our data. I made normal probability plots right there. So step 1, do you have k simple random samples? Yes. We've got 3 groups, adds, Muzak, and classical, and we had 3 samples, one from each of those groups. Check. Were they independent? Absolutely, right? The wait time for somebody who's listening to adds has no bearing on the wait time for somebody who's listening to classical, and so on. Were they normally distributed? That's what we have the plots for, right? They show us that, yes, they are normally distributed. And then the variance, that's the hard part, and we're going to use this rule of thumb. And I kind of wrote it, I think, better than the words that they have up there. Right here, you want your largest value to be less than 2 times your smallest. If that's the case, then you're golden, okay? So if you look at the data sets, We already found their standard deviations. And again, you could have done it yourself, but right there, it's 4.2 and then 2.4 and 3.4. I think I kept more decimal places down here. Yeah, I did, but that's all right. So 4.159 is your largest. 2.387 was your smallest, 2.4, and then classical was 3.4. So you plug it in. You take your largest, which is 4.2, 4.159. Is that less than your 2 times 2.387? Well, 2 times 2.387 is 7.74, which indeed is smaller than that. So yes, we're golden. That's how we're going to verify it. It's a little cheat, but we're going to use it. Cool. Done with that. All right, now let's look at a dot plot, and a box plot of these three variables, so you can kind of see. And I kind of covered over the dots. They're there still, but I just wanted you to see something here. So these are the advertisement dots. These are the classical dots. These are the Muzak dots. Now the means are what I'm labeling here. That's center. Remember that center is your mean, your balance point. So the ads had a mean of 5.4. The classical has a mean of 10.4. And the Muzak was 2.8. Well, let me double check those. Yep, 2.8. Great. All right, now there are two types of variabilities going on here. So there's a variability within the group. There's something called within sample variability. And that's what we already found. There was, for the ads, if you look at these green bar right here, the center was 5.4. How far away are the dots from that 5.4 on average? That's what 4.159 represents. It's the average amount of deviation from that mean. Right? Now the blue one, you can see hopefully that the blue one's much smaller. Right? That's why it has a much smaller standard deviation. There's much less spread on the blue one. It's only 2.4. That's a, oh, sorry. The mean is 2.8. The spread is 2.4, 2.387, right? So the center is 2.8, but how far away the dots are in general from that center is 2.387. And then the red one over here, the mean is 10.4. They would wait on average 10.4 minutes if they were listening to classical music. And the give or take was 3.435. So you can see the green one was the largest, just like we said before right up here. The green one was the largest. That's the ads. And the smallest was the 2.387, the Muzak. Now, there's spread within each of those groups, right? There's the spread for the green line, the spread for the red line, the spread for the blue line. That's what these numbers represent. How much spread there is in each of those groups on their own. Okay? Then there's between sample variability. How far apart are those three lines from each other? 2.8, 5.4, and 10.4. If I take those three lines, those three marks, and I try to see how much they vary from each other, there's another standard deviation there. I mean, if you don't believe me, you could take 5.4 or 2.8, 10.4, right? And you could find the standard deviation of those three. Right? And yeah, there's a little rounding issue here, but that's fine. Okay, it's 3.863. That's how far apart the centers are from each other. And the box plot kind of shows it. So the center of the ads is here. The center of Muzak is down here at 2.8, and so on. How up and down is that variability, right? That's between the samples, not within the sample. So within the sample is like, hey, how spread out is that box plot? Okay, that's within sample variability. Between sample variability is how far apart are the centers of these, well, the means of these box plots from each other. How far apart are the centers of these dot plot lines from each other? All right. And I just wrote it. In other words, how do the centers spread out? So this is how does each of the groups spread out. This is how each of the centers spread out. We take those two values and we're going to create a new statistic called the f-test statistic from them. You take your between sample variability divided by your within sample variability, and we're going to use it to conduct a test. But we're going to have to do it in the next video because we're out of time on this one.